Good morning, everybody. Global economics, and we started to deal with the so-called solo model. This is, yeah, the main long-term model in order to describe economic growth. And yeah, the building blocks of this model are quite simple. So we are modeling production, and the main inputs of production are, of course, capital and labor, and we introduce also this variable A, which is, yeah, the general technology parameter within our model. This describes the effectiveness of our labor. So the better you are educated, the better your infrastructure in your country, the higher is your level of effective labor. Yeah, and then we want to describe our economy over time. And this means especially how evolves capital over time. And this is just described that the dynamics of capital evolvement over time is given by, so the time derivative of capital change in time is given by our investment over time. And then, of course, we have to depreciate our capital stock over time. And this is done in this model with a constant depreciation rate delta. Also, we think that we have an increase of population. Also, this should be constant with a constant growth rate n, and our technology parameter should also slightly increase over time with the rate g. Well, and then, of course, how do we obtain the investment in new capital? This is, of course, and there you can think of the circular flow. This is done in the financial sector, where we put some part of our income. Why? We are given this to the financial institutions via our savings. So just the split, my income every year is splitted into direct consumption and savings. And all the savings within our economy, these savings are collected, and with these savings we can do our investment. So our equilibrium condition is then savings equals the investment. So on this we put then together. So k dot with dot we are describing a time derivative. K dot is investment minus delta times capital stock, and with the equilibrium condition, and we also assume a constant savings rate. We obtain that capital evolves with savings minus depreciation. Well, and now we transform our model into a description with variables per effective labor. So we divide our whole model by A times L. And for this, we assume also that production exhibits constant returns to scale. And remember that this assumption of production exhibiting constant returns to scale is also in line with a description of our economy with full competitive markets, because if you are producing with constant returns to scale, then in optimum your profits will be zero. Okay, and if we divide both sides here of our equation by K over L, by A over A times L, we ended up last week with K dot over AL and S times, and now I go to small variables, so y equals capital Y over AL and small k equals capital K over AL. Well, and this here, yeah, is not so nice, so we have to manipulate this part on the left-hand side in order to interpret our model. So let me write it again. We have K dot over AL equals SY T minus delta K of T. Well, in general, if we are going to variables per effective labor, it would be also interesting to know what is the involvement of K dot. So this would be then the time derivative of capital K over AL. Well, and this time derivative we now just calculate. What do we have here? We have a ratio. Do you remember from school? If you have f of x is u of x over v of x, what is then the first derivative of this function? Is there anybody out there who can help me? If you have a ratio of two functions, what is the derivative? Hmm? Hopefully everybody of you have done this, has done this in school. And I suppose you have done this also as a repetition in your mathematical course here at our university. This is really something what you should be able to do. Calculating simple derivatives. And why is this important? Well, economics is almost always optimizing something. And in order to generally optimize something, you have to be able to calculate a first derivative. So this is u prime times v minus u times v prime over v squared. So, and now we set u is k and v is a times l. So in the first step, we obtain k dot times a times l minus k times, and now you have to be careful, in brackets a times l dot, and this dot is a total derivative of the product a times l over v squared is a times l squared. Well, and then we have this part here. If you have a function f of x is u of x times v of x, what is the first derivative? So if you do not have a ratio, but if you have a product, what is then the derivative? Is now there anybody who can help me? Well, in my course, in macroeconomics, when I have talked about the neoclassical model, and now this is nothing else than the dynamic neoclassical model to describe an economy. We have also done some optimizing processes. And there we have calculated first derivatives. Actually, I hope that I'm not the only one at this university who thinks that doing some math is important in economics. Nobody? So this is u prime times v plus u times v prime. So in the end, we obtain k dot times a l over a l squared minus, and now I set here u is a and v is l times k times a dot times l plus a times l dot over a l squared. Well, the first part is already quite nice because this cancels. So we obtain here k dot over al. And why is this nice? Because this is what we want in the end. This is just the left-hand side of our main equation of the time development of our model. And the next one you will see in a minute is also quite nice, because this I can rewrite as k over al times, so I take one part of the product here, al times al, and dividing just k over one part of the product times, opening brackets, a dot times l over al, not squared, times al, plus a times l dot over al. And why is this nice? In this case, the L cancels, and in this case, the A cancels. And what is A dot over L? Over A and L dot over L. So the change in time of a variable over the variable itself. So what is the change of costs over time over the costs itself? How do you call this variable if you are analyzing the performance of an enterprise? You can write it also like this: change of costs over costs. What is this? What is change of prices over prices? What is change of production over production? I think half of my macro course was about these variables, and also within this course we talked a lot about especially this one. And hopefully you have talked about these two numbers within your term papers. There is something in the chat. Inflation, yeah. And delta y over y, if we think that y is income or can also be interpreted as GDP, change of GDP over GDP is well, this is the main number we are focusing if we want to describe an economy. This is economic growth. And this is, as you said, inflation. So change of a variable over the variable. Yes, economic growth. Thank you. Change of a variable divided by the variable itself is nothing else than growth rates. Well, and we made a simple assumption about these growth rates. If you look at here, constant growth rate of technology in our country and constant growth rate of population. So the nice thing is then that this is G and this is N, the growth rate of population. And technology growth rate. So then in the end, we can write here that taking all this together, that we obtain K dot equals capital K over AL minus K over AL times N plus G. So, and here we directly see that this is just capital per effective labor, so small k, and then we end up with k dot over AL equals small k dot plus k times n plus g. And this now we feed in our main equation of our model, and we then obtain k dot equals s y minus delta plus n plus g times k. And this is the main equation of motion of the Solo model. So this took some time, but in the end we have a nice little equation which we can interpret. So let's take this one. Copy. And this we will do graphically. So let's write down in our diagram on the vertical axis total production, and our savings, and on the horizontal axis capital. So remember, y was production of capital per effective labor equals 1, and I think I have written small f for this one, or no, I didn't. No, yes, here I have it. So, and if you remember, at least your macro and micro course, and hopefully also the introduction of general business administration. There you should also have seen it. What is general assumption about the neoclassical production function? How does it look like? Can you describe it? You can also use your microphone. Or in macroeconomics, we have done this looking at the absolute values. So f of capital K and K. Oh. Well, this semester we will talk about this next week or on Thursday in macro. But I think here are also some guys who have already listened to my macro course. But this production function, this you should have seen also in other lectures, at least in microeconomics. Anybody? Well, the first assumption is, of course, the larger the input, the larger is production. This means we have a monotonically increasing function. But then the second assumption is that the higher the production level, the lower will be the additional output given some unit of input. And this means that the production function is right banded. So if you have a low production level, moving from 1 unit of K to 2 units of K, you have, so to speak, a large additional output. And if you are already at a high level, let's say 10 to 11, then the additional output is lower. So delta Y2 is lower than delta Y1. Well, and this is the general assumption that the higher your development of your society, the more difficult it is to add something. Well, and if you look at the different countries in the world, what you have done, All of you have different countries. Then you see that developing countries, countries with a relatively low level of income, have in general higher growth rates than highly developed countries. So within Europe, in the United States, the growth rates, we are quite happy if we have growth rates between 1 and 2%. If you look to Africa, if you look to Southeast Asia, and so on, then you find their growth rates of 3, 4, 5, 6%. Or in the highly developing process of China in the beginning of the millennium, China has been grown by 10% and more. Or if you look right now to India, then India is doing quite well and has growth rates between 5 and 10%. So this is our neoclassical production function. This we find also here, S times F of K. So then we just draw this total production. So this is F of K times equals Y of K. Well, then if S, our savings rate, is constant and S is of course smaller than 1. We do not save 100% of our income. Relative to f of k, how does S times f of k looks like? Multiplying f of k with a number smaller than 1. So if this number here is 10, multiplying 10 with a number smaller than 1 is a number this would be 10.
It's a number lower than 10.
Of course, it's a number lower than 10. And so every number here on our graph is then lower than the level itself. So S times f of k then looks somehow this. And since it's a relative decrease, the distance for a low level has to be lower than for a high level. So this would be then S of f of k. And then we look at this one here. This is some positive number. So how does look like f of x is a times x with a larger than 0? What kind of function is this then? F of x equals 3 times x. What kind of function is this? This is, I think, school, class 7 or 8. This is a linear line passing through the origin with slope a. So let's draw this line. So this is n plus a delta plus n plus g times k. So why do I draw these two functions here? So the two functions of the left-hand side. Well, the cut of this is where we do not have a change of capital in time anymore. And therefore, we call this point the steady state. Within this steady state, the left-hand side is 0. So here we have S f of k equals n plus delta plus g times k. This means k dot equals 0, no change of capital in time anymore. And this is therefore then called the steady state. Well, and also we can argue if we are at some k smaller than k star, if k1 is lower than k star, what do we have? Then, of course, S times f of k is larger than delta plus n plus g. So there is still a gap to increase k to invest. So in this part, we have a force that which is driving ourselves into the steady state. And if we take some we invest and economy is driven into steady state k star. If k2 is larger than k star, what do we have? Then delta plus n plus g times k. So especially the depreciation delta times k is larger than our savings S times F over K. So in this case, we have a, so to speak, overinvestment. And this means due to the time development, K dot is negative. This part is larger than this part. And so we start to de-invest. So also in this case, we are driven into the steady state. We de-invest. And also economy is driven into the steady state and overall, and this is the reason why this steady state is so interesting. steady state is stable. Remember here also our macro models, there we also discussed the equilibria, or in economics in general, if you remember the market diagram, supply and demand, that this equilibrium is also stable. Okay, and now we can do, so to speak, politics in our model. Let me redraw this one. Uh, f of k s times f k n plus delta plus g times k s times f of k and f of k itself. So what happens if S is increasing? What happens then in our diagram? Let me draw this in red. What happens if this number is increasing? If we have not a savings rate of, let's say, 10%, as we have it in Germany right now, but 15%. Well, just the opposite, what we have talked about a minute before. Then, of course, this function s times f of k is bending to the left. Here, s prime times f of k with s prime larger than s. Well, what happens? Our steady state is moving outward. Then k star is increasing to k star prime. And what happens if n, delta, or g are increasing? So if this number is going up, Let me take this in green. Well, this means that the slope of our linear line is increasing. And increasing the slope of a linear line means that it is turning to the left. Yep.
Well,
Okay.
I would have said it would get steeper, but it's
Yes,
basically what you
it
said.
gets deeper. This is the same. Yeah. Anyway. So in this case, it would maybe look like this. N prime plus delta prime plus G prime times K. Oh, take this thinner. Well, and then of course we see here our cut is moving to the left. So then K star is decreasing to double prime. K star double prime, and here we write n over larger than n, delta larger than delta, and G prime larger than G. Well, what does this mean? Especially if n and delta, so if we have a larger population, then since we are calculating here, remember, K is K over AL. So if population growth is larger, then we have a larger population. And this means, of course, that the relative number, capital per effective labor, is going down. The same here if A is increasing. So this is not very surprising. And also if the depreciation rate, delta, is increasing, what does this mean for the economy? Then we need every period more production to just hold our level of capital in our economy. If the depreciation rate is 10%, we need only 10% of our next period production to hold the level. If this is increasing to 20%, the depreciation, then of course we directly have to move a larger part of our next term to production to just hold our level. Well, so in this model, we see that an increase of especially saving is, so to speak, good for our economy. And if we compare this, what we have also talked within this lecture with the Keynesian model, so especially here, as going up, we have an increase of total income y, since y is just a function of k. So if k is increasing, then of course also income y is increasing. Compare this with the Keynesian view. There, remember the Keynesian cross. Looking just at the commodity market. YD, Y, Y equals YD and YD. Here we had equilibrium income. What happens if the savings rate is increasing in this Keynesian model?
Spending decreases.
Yes, and which function in this, or how does this function changes here, the total demand function, if savings rate is going down? What is the slope of the demand function?
Going down or going up? The saving rate.
The saving rate is increasing.
The saving rate is increasing.
What happens then to total demand in the Keynesian view?
Yeah, well, the total demand decreases, but
Yes, great.
yeah,
Because the slope of this function is the marginal propensity to consume. And if the savings rate is going up, then of course the consumption rate is going down. So then we would have here S, so I take this also in red. Then the slope, oh, where is it? Why hasn't worked? No. Then this is going down. And then income is decreasing. Well, and now remember, both models, the Solo model and the Keynesian model, are just describing our economy. And of course, also this, as you have learned in my macro course, this equilibrium condition, y equals yd, is nothing else than I equals s. And if you remember, where do I have it? Here. Also, the equilibrium condition in the Solo model is nothing else than I equals S. But both models are coming to totally opposite interpretation of the effect of a change of the savings rate in the economy. Well, and what is the reason? The reason is just, or are just my assumptions, which I make. How is an economy functioning? The Keynesian view focuses more on the demand side. And this means demand, mainly consumption, means, well, if this demand is going up, if I directly consume a large part of my income, then this pushes the economy. And of course, no price effects, and therefore I can directly push my production via more consumption. Well, on the neoclassical model, this focuses much more on the supply side, especially here. This is maybe the main building block of our model production, f of k, depending on k, depending on capital. Well, and how do I obtain much capital in the next period if I save a large part of my income? But I think it is interesting that here, just within two models with the same equilibrium condition, you see just this split in the view on the economy. Okay, then let's talk also about what is maybe a little bit surprising is that, let's take this now in the next color. Let's take purple rain. That steady state is going down if G is going up. But of course, this more or less then means that we are more effective in our production. So we need not that much people, so many people as before if our technology level is higher. But what we also see is K star, oops, star, not dot, is capital K over L. And this we can rewrite to A times L times K star is K star. And then we can ask, how is capital K evolving over time? For this, we just calculate the log time derivative of K. Remember this we have done in the macro course, and we have looked at the quantity theory of money. So what we do is ln of K equals ln of A times L times K star. Another math lecture, log of X times Y. This can be rewritten as the sum of the two numbers. So taking logs in economics is a nice thing in order to linearize dependencies, products, and ratios. And very often you have variables which you just multiply within economics. Think of revenue, price times quantity. This is just a product. Or interest rates times capital is capital cost. Wages times labor is labor cost. So this is then ln of A plus ln of L plus ln of K star. And now let's take on both sides the time derivative. Why is it nice? If you have f of x equals ln x. What is f prime of x? This is just 1 over x. So what we obtain here is then k dot over k equals a dot over a plus L dot over L. Well, the definition of steady state is that there is no change in time anymore. Steady state is constant, and the time derivative of a constant is, of course, 0. So, and this we had on the former slide. This is G and this is N. So G plus N. So capital is growing by G and N. And so if we actually look at this dependence here, that capital over time is mainly driven by the growth rates of technology, then you see also here this neoclassical view. So if you want to push your economy, what you should do is just pushing or is just to improve infrastructure, to improve um, digitalization, to improve education, to improve the framework of your society. So then we have a little bit of time left. Then we can do some last interpretation of this model. Again, oops, let's do this in black. N plus delta plus G times K. F of K equals Y and S times F of K steady state. Well, now we can ask how to maximize consumption. Well, in general, we have Y is consumption plus savings. But for savings, we said we have a constant savings rate, so S times Y. Sorry, we have to deal, of course, again with our small letters, since we still want to interpret it in numbers relative to effective labor. But from our main equation, we know K star is S times Y minus N plus delta plus G times K in steady state, we have Sy equals n plus delta plus g times k. So we can rewrite this to n plus delta plus g plus k. And now we obtain consumption is total production minus n. Total production is of course also depending on k. Oops. Plus delta plus g times k, and therefore of course also consumption is a function of k. Mathematically, what are we doing if we want to maximize a function? What do we have to do? If we have f of x and this we want to maximize, what do we do?
First derivative.
First derivative, great. So c prime of k equals then production, so y prime of k, and the derivative of this linear line is what? F of x is ax. What is then f prime of x? 5 minutes, then we are done. And no derivatives anymore. F of x equals 3 times x. What is the first derivative? This would be 3. So a. So we, of course, end up just with the slope here. So n plus delta plus g. And what is the condition? What has the first derivative to be in the maximum?
Equal to 0.
Equal to 0. Great. So we obtain then y prime, oops, and yeah, y is of course the same as our production function f. So we obtain y prime of k equals n plus delta plus g, or of course f n plus delta plus g. And if we know our production function, then solving this for k gives the capital stock for maximum consumption. And therefore, this is then called the so-called golden rule, capital stock, because then the society has the highest consumption level. KC star, and this is the so-called golden rule capital stock. Well, and as we have it quite often, where do we find this condition in our diagram? So here f of k s times f of k and k. This would be the case if in this point we have that the slope of our linear line is equal to the slope, almost always, almost, sorry, then it would be better I draw this in another way. We have to have the same slope and then like this. And these two have to have the same slope. Well, graphically, we more or less see this directly because in order to obtain the consumption is just the distance between total production and savings. So always here the distance between these two functions is consumption. And so this would be C, let's say golden rule. C golden rule is then of course given when the distance between these two functions is maximized, and this is maximized when the slopes of these two functions are maximized. Uh, the slope of these two functions are the same. Well, I think 1 or 2 will be in the macro course on Thursday, and then you will more or less see this picture when we are doing profit maximization. So this is just a minute. So compare with profit maximization. Because what do we have in profit maximization? We look at the revenue. P is Px minus, or not X, let's say K times R. K and X is our output. So this is just F of K and L. So P times F of K of L also looks like this. And our car are our capital costs. And this is PF. And then you also just want to maximize the distance between revenue and costs. And this is then, of course, in the part when the marginal product of capital times prices equals interest rates. This hopefully you also have already, you has also already seen in other courses. Yeah, that's it. Of course, with this solo model, we can do much more, but this should be just an introduction on this main growth model. And of course, in the end, what we have derived here is then, and this is done in many, many econometric studies, that we can explain the different levels of economies throughout the world via this description with the solo model, and that in the end, the differences in the development of the countries are depending on their technology level. Okay, that it was for today, and then we are also done with the, so to speak, a normal part of the lecture. And the next time we meet, or I meet you to see your presentations on 16th of December. Thank you very much.